Greetings, I'm Yvonne, staff for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. This is a particularly exciting era for astrophysics when a combination of brilliant scientists and advances in technology are providing unprecedented discoveries about our universe. One scientist to watch is Mark Vogelsberger, Associate Professor of Astrophysics at MIT. Dr. Vogelsberger is famous now for very complex models of the early universe, a period inaccessible to telescopes. He'll explain what these models predict about the earliest universe, stars and galaxies, and the role of dark matter and other factors in the early universe as well. Welcome, Dr. Vogelsberger, and thank you very much for joining us. And if you wouldn't mind, could you give us a little background about that very dark period after the Big Bang, where before we really have atoms and so on, and up to the reionization?
Yep, sure. First of all, thanks for having me. Yeah, so the standard picture that we have about the evolution of the universe is this picture where we have, this Big Bang and then an inflationary phase, and then slowly, in the first couple of minutes, all these important particles are building up, and then there's one important phase that you just mentioned, where the so-called cosmic microwave background radiation is released. So that's the time when actually the coupling between what we call baryons, so the atoms or the protons and the electrons essentially, and the photons, if this coupling gets weaker because neutral hydrogen forms, so the electrons go together with the protons, then light can escape. And so that's the one of the very first very important times in the universe, because we can also observe this cosmic microwave background radiation.
So finally we can see it a little bit.
Yeah, exactly. So there have been a lot of missions to observe this, and you can constrain or gain a lot of information out of that and constrain cosmology through that. Now, after that time, the universe was indeed rather dark because there have not been any stars yet, and which are the sources of light. And so this took a while until the first stars and the first galaxies actually formed. And once these formed, then they emit this light, and this light is then capable again of ionizing, for example, the hydrogen. So that is then the epoch that starts, which we call the epoch of reionization. And for that you need these first stars. And before that we have kind of the dark ages where really no light is there. There's not much happening, and but that initiates a new phase in the universe, which eventually leads to a total ionization or nearly total ionization of the hydrogen in the universe.
Okay, so with the reionization, then the atoms are fully formed, the things are starting to develop. But before that period, you have a long period of like 400,000?
Yeah, so the cosmic microwave background radiation is kind of emitted around 400,000 years after the Big Bang. And then there's a long time, tens, hundreds of millions of years until the first structures are actually forming, the first stars. And they then light up the universe again, and this ionizes then the hydrogen again.
Okay, so and this is the part that is of great interest now, because I guess there were so many unanswered questions, and so you have done these simulations, and I'd like to ask you now about the simulation. Why is that necessary? Because what makes that an essential part of figuring it out?
So we have, of course, a general framework, how we think how structures form, but if you really want to understand this in detail, really understand how, for example, the reionization happened, how these first stars, these first galaxies and all the structures are forming, then the underlying equations become very what we call nonlinear, so you cannot just simply solve them with pen and paper, so the equations become rather complicated. And so that's the point where we need these computer simulations. And these computer simulations then discretize these equations and can follow the whole evolution actually until the present day. Because they can treat these nonlinearities and the more complex physics that's happening. And that is something that we cannot do with pen and paper, and that is something where we need these simulations.
Okay, two things. So you couldn't do it on pen and paper because it's so complicated. And then there are many, many unanswered questions about that period. And then on top of that, Is this recent? I understand that this took some computer power that is almost off this planet. It's so huge to put this together. Is that recent? You'd have to wait for that.
So these simulations started a while ago. So people have tried this already decades ago, or have done this already decades ago. Now, what's of course happening, with the improvements or the increase in computing power, we can do better and more refined simulations. And this has reached now a state where, modern so-called cosmological simulations are really capable of, giving us an insight into the early formation of galaxies, but also the largest structures like clusters of galaxies and all these structures that we have in the universe with really great detail. And what we also achieved over the last, say, 5 to 10 years is that many of these predictions of these simulations agree remarkably well with what we see in the real universe. So that is something that, for example, was not possible, say, 20 years ago or 15 years ago. So this is a more recent thing of the last decade.
Right. One more thing about making those simulations is that apparently that's a very complicated thing, and you've gotten a huge amount of press about that, about yours. So we'll come to that. But in these kinds of things, so I don't know anything about this beginning of the universe, but we have these different hypotheses for that reionization period and how galaxy stars are forming. Do you make up different ones to test, so to speak? Do you see what I mean?
Yeah, so that's essentially one important part of the work. So, traditionally in physics, you have a theory and you have experiments to test it. Now, the universe, we cannot easily do these experiments. The only thing we can do with the universe is observe. So what we do in terms of the experimental part, we can try different theoretical models in these simulations. And one interesting part here is, for example, what happens if we change the properties of dark matter? How do the galaxies change? So there are different ideas of what dark matter is. It hasn't yet been detected. It's just a hypothetical particle, but the properties of the particle can be different depending on what theory of dark matter you invoke, and this directly has consequences for the structure of the galaxy. So you can actually simulate different universes and then compare to the real universe and, so to speak, constrain these dark matter models.
Okay, so you really can test quite well with those simulations. It's not one size fits all.
Right, yes.
Right. And you brought up the dark matter issue, and you have a theory about dark matter too, but this was very important in the beginning in developing the galaxies and so on.
Yeah.
Then I want to make sure we cover those things. That I come back first of all to the simulation itself, and I think the simulation that we're going to look at includes the dark matter, but we'll talk about some more there. The Thiessen simulation, which made you famous there then, and followed by a couple of more now. This has you have a very nice video clip that MIT has made, and Center for Astrophysics and so on. Could we have a look? Could you walk us through that?
Yeah, let's have a look at this. So this is actually a visualization that has been made by one of my former postdocs, Aaron Smith. So what you see here is the very early time. So on the right, you see the time since the Big Bang in millions of years. So this is 500 million of years. And then we visualize the photons in this universe as it emerges from the galaxies, but also the gas. So what you see, for example, now is the large-scale structure of the gas. You see this filamentary structure. And so at these nodes where these filaments meet, there's actually the place where the galaxies are actually forming. And so you see this nice cosmic web-like structure, which is a thing that these simulations predict. And by that time that we see now, this is now the time when the universe is actually is kind of fully ionized. So this is the end of the epoch of reionization. And so this simulation, as you mentioned, includes dark matter, but also the gas and the stars and the galaxies. It's all included. So this is a project that has been led by Aaron Smith, Raoul Canan, and Enrico Garaldi. So they really put years of effort into that simulation.
I was going to say, this took some years, evidently, to do this kind of work, even though we're looking at it in less than a minute.
Yeah, it compresses a very long computing time. So this takes...
A couple of things in that simulation is that it's interesting that you have these like threads, filaments through here. Could you explain that the galaxies? First of all, we only have hydrogen at this point, hydrogen and helium, right? When they're forming.
Yes. Yeah.
But the other is that they're not all over the place. They're formed, it looks like, on these lines. Could you explain what that is?
Yeah, so this is essentially a consequence of this gravitational collapse that's happening. Yeah, so the structure formation is all driven to lowest order from gravity. Yeah, so you have initially in the universe a so-called density field where you have high density regions, low density regions in dark matter, and then the high density regions, they start collapsing. Yeah, and this collapse leads to this web-like structure. So you have different modes of collapse, and some of the collapse leads to these filaments, and where these filaments cross, you have then so-called dark matter halos. Yeah, so these are nearly or close to spherical dark matter objects, and at the centers of these dark matter halos, we see then the galaxies. So this is where the galaxies sit. So also the Milky Way itself is embedded in a larger dark matter halo. So that is the current paradigm that we have for dark matter. And dark matter is really crucial as kind of a backbone for structure formation.
I wanted to ask that next. You wouldn't get this
structure
you wouldn't get without the dark matter.
Yes, you wouldn't get the right structure for the galaxies, you wouldn't get the right clustering of galaxies, so the distribution of galaxies in the universe. So a lot of things wouldn't work out if you would not have dark matter.
That's a real interest to figure out what that dark matter is.
Yes, it's really the key ingredient for structure formation, dark matter.
Okay. The other thing is that apparently these galaxies and the stars, are they different sort of from what we see today? First of all, size. I don't know about how they form, if it's different from what we would.
Yeah, so the early galaxies, so galaxy formation essentially starts, or the picture is that you first form small galaxies, and then they can merge, and then they build larger and larger galaxies. So for example, the largest structures that we see today are these clusters of galaxies where you have hundreds or thousands of galaxies in a huge structure, but those form rather late. So you start early with smaller galaxies, and then, as I said, they merge together. So that's kind of this picture that's also driven or happens because of the dark matter. Yeah, so this is because the dark matter also clumps first on small scales and then on larger scales. So that is kind of the underlying picture.
Okay, so there's like a qualitative difference between these structures in the early formation, and as opposed to as the universe evolves.
You start small and you get larger towards the present day.
Right. And now, of course, stars are more complex. When they explode, then they release all these elements, but they didn't then.
Yeah. Also, the chemical composition of the universe also changes, because initially, as you also said, you have just helium and hydrogen mostly.
Right.
Yeah. And the stars are then responsible of creating other elements like oxygen and carbon and so on.
Right. Yeah. But that doesn't happen immediately. I get that.
No, you have to go through nucleosynthesis essentially in the stars. So they create then these elements. Yeah.
Okay. Is it okay to ask you about that dark matter theory that you have at this point? Because if you can't build this at all without the dark matter, then how did you come to your theory, and what is it?
Yeah, so there are many different theories on dark matter.
Yes.
So the standard paradigm is so-called cold dark matter, which is a very generic theory. But then there are others, too many to list them. But one interesting model is, for example, so-called self-interacting dark matter, where you have self-interactions or kind of collisions between the dark matter particles. And another one that over the last couple of years became, people got more interested in this, is so-called fuzzy dark matter.
Yeah.
So this is an idea where you have a very, very light dark matter particle. 10 to the minus 21, 22 electron volts, so really, really light.
Really big.
And so this then leads to rather different effects in terms of the dark matter behavior compared to cold dark matter. So specifically, this dark matter particle is so light that it has some quantum properties. So you get quantum effects on large scales. So this sounds a bit counterintuitive, because quantum is always, we think about small things. But the properties of the particle are such that you really get quantum effects on cosmological scales. And so you get, for example, quantum interference. You get at the centers of galaxies, or at the centers of these dark matter halos, you can have quantum pressure that changes the overall distribution of dark matter in the centers. So there's a lot of interesting things happening in this fuzzy dark matter. Likewise also for the self-interacting dark matter. So they all lead to distinct imprints in the structure that are different from cold dark matter. Now, one of the interesting questions is then, can we constrain these models, rule them out? This is where the simulations become really instrumental, because that's actually one of the only ways to really properly test this in terms of comparing to astronomical observations.
Right, you can't just go out and get some dark matter and look at it.
Right? People are trying to, of course, detect dark matter in lab experiments since many decades, but this is very, very challenging because it's so weakly interacting. So this hasn't yet been detected. But another way to look at it is really to compare astronomical data to theory predictions from simulations.
Okay, so it can be, you can try this out with simulations. And as you mentioned, there are a lot of theories about what dark matter is. So you could do this, and especially now maybe with this very advanced, like the James Webb and so on, the more sophisticated technology these days.
Yeah, exactly. So the idea is really, you take advanced observations with James Webb Space Telescope or other telescopes and compare these observations with what the theory predicts. And indeed, it's rather easy to come up with a dark matter model that leads to significant disagreement with the observational data. So these models are ruled out, and a lot of models have already been ruled out based on these things. So there's still a large number of models left that is feasible. And so, things like James Webb and better observations will allow us to constrain this further, combined with the simulations.
I see. Okay. In this period, you also have, if I may ask, these enormous black holes. And how did that happen at the beginning? Is that part of your simulation? Is that essential to the development of the universe?
Yeah, so indeed there are these so-called supermassive black holes at the centers of galaxies. Now they are not so crucial in this Thiessen simulation that we just saw. They are not so relevant for the times that we explore to drive the reionization process. But later on, they become very important in terms of regulating the growth of galaxies. So it's a very important mechanism that people have found to actually regulate the so-called star formation in galaxies. So if you don't have these supermassive black holes, you essentially produce too many stars in some types of galaxies. So the idea is that these supermassive black holes, they can create a so-called accretion disk around them, and that will effectively couple to the gas around them and, for example, heat up the gas or put some energy in the gas, and that can suppress the formation of stars. Because to form stars, you ideally want to have high-density cold gas. So if you heat it up constantly, it's more difficult to form stars. So these supermassive black holes, later in the evolution of the universe, become crucial to regulate the star formation.
That's interesting. Like they're like stabilizing forces.
Yeah, exactly. They lead to a so-called feedback cycle.
But it's important, like a head predator or something like that.
It's a regulating mechanism.
Exactly. Yeah. That is most interesting. I asked about the black holes because I thought that they had thought there were enormous black holes early in the universe, and I've never understood it myself.
This is still an open question, actually, how these, again, there are different theories, but it's difficult to form black holes with a certain mass early on.
There isn't that much, it's not out there.
Because you have to have some model how they accrete and so on, how they grow, and they can also merge together. But there's still a lot of puzzles how they actually get their masses early on.
Exactly, because then that's a great comfort to hear that, because I've never been able to understand that. Now, there's another issue that I think your simulation takes care of, and that is the light. So the early light apparently couldn't travel that far. I'm not sure what that's about, but the light itself, radiation.
Exactly. So as we discussed in the beginning, there's been this cosmic microwave background radiation. So that's the first time when light can travel. Before that, what happens is you have these free protons and electrons and the photons, so the light. And now these photons, they scatter off the electrons, and that leads to a very tight coupling between the electrons and the photons. And since the electrons are also coupled to the protons through the electromagnetic force, everything is tightly coupled, so the photons cannot really escape from this so-called baryon photon plasma. So the only way they can escape is at the time of the recombination, because then the electrons go together with the protons to form neutral hydrogen, and then this electron-photon scattering is not happening anymore, and then the photons can get out. Yeah,
right.
so that is the first time where photons can really
Okay, and
travel
after
freely.
that, light is light, or radiation is radiation. But I see now what the
Yeah,
difference.
I mean, it has also been radiation before, but it was tightly coupled
but that's
into this
and
plasma.
messier, I guess,
exactly.
messier. The other thing is that I think you take up is the dust factor, and if you could explain the cosmic dust.
Yeah, so I said before, we start in principle with helium and hydrogen in the universe, and then the stars lead to nucleosynthesis to produce heavy elements. But then you can also have, these heavy elements, you can also form compounds of these elements, which eventually lead to certain forms of so-called cosmic dust. So that's a small component in galaxies in terms of the mass budget. So, for example, the Milky Way, this is about 1% of the mass budgets in the interstellar medium. But it's very important, at least for the evolution of later galaxies, to regulate for the physics of these galaxies. So it can impact, for example, the cooling of gas, and it also interacts a lot with the radiation. So if you look at a galaxy, for example, you see sometimes these dust lanes because it obscures the radiation. So it's a small component in terms of the mass, but it has a lot of interesting and important effects for the galaxy evolution. And so what we have in Thiessen is there's a simple dust model included that we can actually follow this dust. It's not so important for the overall process of reionization, but especially later in the evolution of galaxies, this becomes important, this dust component.
So you incorporated that. And then is it different, whatever that dust is it different in that very early stage than what we would see in terms of what we call cosmic dust today?
So there are different types of cosmic dust, that's true, but in the early phases there's actually very little dust. So it takes it takes a while to build up all this dust, because you have to go through all these stellar evolution phases and so on. And there are different types of dust in the universe around, like silicate-based dust and other dust forms that we can observe. But in the early phases, it's still all rather simple in terms of the content of the universe.
I see. But it's these different factors that you've had to insert in your simulations, and I assume these are in all simulations. They have these factors, but they then model things differently to test it against reality. So we ask them the gas filaments, and then for the magnetic field, is it always there? Was it always there, these magnetic fields?
So the simulation also includes magnetic fields. Now, how these magnetic fields come into existence is, again, a debated issue, so where they actually come from. But once you have these magnetic fields in galaxies, for example, they can get amplified through so-called dynamo processes. So if you have turbulence in galaxies, for example, you can amplify these magnetic fields so that galaxies like the Milky Way, or also galaxy clusters, they have some magnetic field that actually can be measured also through something like Faraday rotation measurements. So you can constrain these magnetic fields, and again, you can then compare, the predictions of simulations, what magnetic fields they predict to observations. And surprisingly, despite the fact that we don't in detail understand the formation mechanism of the magnetic fields, the fact that they get so strongly amplified throughout the evolution of the universe makes them very insensitive to the seed magnetic field strengths, so that despite the fact that we don't have a good understanding of their formation, still the predictions agree remarkably well with the observations, for example, in the Milky Way or also in clusters of galaxies.
So that's all really very clear.
I mean, there's still a lot of problems associated with it, but at least in this simple comparison, there's pretty good agreement.
Okay. Can we focus a bit on constructing the simulations themselves now? Because this is almost a work of art, apparently. You've gotten, as I said, a lot of attention for this, and your team that that has worked on this. And I would like to get the what the difference between the Thiessen project and then the subsequent, or
Earlier,
there was an earlier
yeah.
one, and then now you're working on expanding that one. Can you tell us about these? How do those evolve? And I'd like to know also, like, how do you put those things together?
Yeah, I think the first thing to realize is really that there's a lot of people involved in this.
Sure,
Yeah, so,
absolutely.
There's always a team of 10, 15, 20 people that work on various aspects. And there are different challenging aspects. So one really challenging aspect is to take the equations, the physics equations, and actually put them on the computer. Yeah? So this discretization, and then also making sure that you exploit the computational resources as well as possible. Yeah? So these computers today can have millions of compute cores.
Yes.
And the reason why they are so fast, or why they solve problems so fast, is because you distribute the work on each of these cores. Now, one of the main challenges, and this is really a very difficult task, is how you distribute this evenly. Yeah, so you have to distribute it very evenly, because otherwise, if one core has to do a bit more, then it will slow down the whole calculation. And so this is an art by itself. And indeed, there's only very few people in the world that can do this really efficiently. So we have very good collaborators in Germany who are really extremely good in doing that. So that's one important part. And then the other thing is you also have to put in a lot of these physics. You mentioned the supermassive black hole, the dust, and all this. So each of these is kind of a little module in this simulation code. And so typically you have then a couple of people implementing this and testing this. And at the end of the day, you put this all together, and then you start, first of all, simulating smaller universes. So it's just a small patch of the universe, maybe tens of millions of light years across or something like that. And you see how the model behaves, and specifically how the predictions of that model compare to what we see in the real universe. And if usually at the beginning a lot of things don't work out so well, so there's a lot of calibration steps and tests involved. And at some point you reach a state where the predictions are really in very good agreement with what we see in the real universe, and then you scale this up to a larger volume. So and that is then, for example, what we did on Thiessen, or in the simulations before, like Illustris and Illustris TNG, and many of the other simulations. But it's really a multi-year, multi-people effort.
I was going to say, the computing sounds staggering all by itself, but and I'm sure that will be a field, these emergent kinds of simulations based on emergence of things. But this was the largest, or one of the largest simulations made. Was that Thiessen?
So you always have to be a bit careful with these.
I understand. It was big.
It's big. I mean, the point is, I think in terms of reionization simulations, it's one of the larger ones. So it's really pretty much state of the art, also in terms of how, in what detail we can resolve the galaxies. But this field is constantly evolving. So in 2 or 3 years, there will be larger simulations available. People are pushing this always.
Well, I'm sure. And every time you do one step, then it makes the next step possible. You can't start out that way. What are you working on now?
Actually, we're working on some follow-ups of Thiessen, specifically my collaborators. So Thiessen is this large volume where we simulate on a patch of the universe. But now what we want to understand is the very detailed properties of these very early galaxies. So what we do now is we do so-called zoom simulations. So that means we focus all the computing power on one galaxy or a handful of galaxies. And the advantage then is you can resolve the internal workings of the galaxies much better. So that is something that's a Thiessen follow-up that will hopefully come out in a year or two, that we are very interested, because then you can resolve also the radiation processes in the galaxies in more detail. You can resolve H2 regions, and you can also make more specific predictions, maybe for JWST and other things. So that's kind of the next step that we're currently working on.
That's going to be rather busy.
That's true.
I was going to say, it seems as though there's still many questions about galaxy formation. It's not like one fixed recipe, apparently, even, I say now, I mean in the more recent universe, not that earliest universe. So there must be quite a few questions about how this got off to start anyway.
Yeah, that's true. I mean, the point is, I mentioned to you we have these different physics implemented in the simulation, but
Yeah.
to be honest, a lot of these descriptions are still rather simplistic and they have uncertainties. And we also have to improve these models to understand the physics better. So there's still a lot of things to be done.
One last question. With the James Webb Telescope now, is that considered helpful? Will that help you to confirm or your hypotheses?
Yeah, there are many fronts where this telescope is helpful, but one important thing is, for example, that the simulations can predict how many galaxies there are at a given time of a given luminosity in the universe, and JWST can actually probe this at very early times. And so this, coming back to the dark matter point, is a way also to potentially constrain the nature of dark matter, because different dark matter models predict different numbers of galaxies.
Wow, what an exciting time to be doing this work. You just got it right on the really.
Indeed,
And now the rest of your life, you're going to be very, very busy. But Dr. Vogelsberger, it was wonderful to talk to you about this. I just wish you the very best with this project. I'm sure we'll hear lots about it.
Yeah, thanks a lot for having me.
Thank you. Thanks. It was most enjoyable. Good luck.
Thanks. Thank you.